As you know, the title of this set of lectures was Quantum Field Theory with and without Planck constant. Today we will study physics of quantum mechanics and how Planck constant appears. Let me tell you what would be the outcome. First, quantum mechanics does not need Planck constant in its definition. Second, Planck constant is the measure of how close quantum mechanics is to classical mechanics. And of course, we will consider examples that would illustrate this idea. Later, we will generalize it to quantum field theory. But today and on Friday, we will study only quantum mechanics. Okay, so the pioneering work appeared in 1930 by Dirac, who said quantum mechanics is a new physics. Everything we knew before should be reconsidered, such that in some limit we would get classical physics. So this step is much more revolutionary than the step made by Einstein with relativity. Because in relativity, people say, okay, we replace space times time by space-time. Okay, it is important, but it's not a drastic change. In quantum mechanics, the structure of physics was completely changed. So let me explain what was the greatest change made by Dirac. First, state of the physical system. It is a philosophical category, state. So previously, it was a point on a phase space. In examples, coordinate and momentum of the particle. Now, the state is a projective line in a Hilbert space. So what do we mean by Hilbert space here? Hilbert space, could be a finite dimensional vector space with Hermitian inner product or infinite dimensional vector space with such a product. Example of such Hilbert space is a space of functions complex on a compact manifold with the inner product given by, and here I have some measure, and we call it F1, F2. Of course, the example with finite dimensional vector space is simpler, so we would concentrate on this example. Projective line is a class of equivalence of vectors traditionally called psi's, under psi is equivalent to lambda psi, where lambda belongs to C star. Let me make a remark. In original formulation of quantum mechanics, people were using a bit different language. Dirac said, state is just a vector psi that belongs to the Hilbert space with psi equals to 1, such that psi is equivalent. But it is the same as to consider projective line. Example, CP1 may be considered as C square minus 0 over C star. So here we have projective lines. Or it may be considered as S3 over U1. S3 appears as Z naught moduli square plus Z1 moduli square equals to 1. And that is this condition, that norm of the vector is 1. Then we take e to the I5 identification. Okay, so this is the concept of state. Then we need to define the following. First, how state is changing in time. It was obvious. It's called dynamics. And the second thing was not obvious before. How do we see state in experiment? If we understand the answer to questions 1 and 2, we would say that we may predict results of experiments in future from result at initial time. I want to remark that in classical physics, 2 was not considered as a problem. We said that we just observed coordinate and momentum of the particle. In general, classical mechanics, we may say that we observed functions on the phase space. So, in classical mechanics, state was a point, observable was a function, result of observation, evaluation of the function at a point. So nobody even tried to formulate it. It was so obvious that it was never formulated explicitly.
If we consider statistical mechanics as part of classical mechanics, at least what's now called classical statistical mechanics, then was it kind of formulated there because the state was not a point anymore? It was also a distribution in a way, and evaluation was not so trivial. What do you think?
So statistical mechanics is somewhere in between. Actually, foundations of statistical mechanics were coming out of quantum mechanics. And it's an important point. Actually, I was on the conference where Edward Witten and Ludwig Fadeev and I think Maxim Kontsevich were given prizes. And on that conference, people were thinking about what was statistical mechanics before quantum mechanics. So what was the origin of probability? And people explained that it was kind of philosophical problem. What causes probability? Just to give you an idea how strange was the understanding of statistical mechanics, I'll give an example. I will not write it in words. As you know, in classical mechanics, everything is deterministic. So the question was, what is the origin of indeterminacy, of probability? And people were even thinking that the origin of probability is in the will of live creatures, like that when bird was flying over the ocean, bird can decide where to go. And this was considered as the origin of indeterminacy. But what if we have an ocean and have no birds? So this I'd like to write down. Statistical mechanics had no foundations before quantum mechanics. It could be considered as a formal mathematical scheme, but it was not derived from the classical mechanics. So it is my personal opinion. Moreover, people were thinking if it is possible to derive quantum mechanics cannot be derived from statistical mechanics. And there are even so-called Bell experiments showing this. So this was my remark on statistical mechanics. So let me go to quantum mechanics. And here, the greatest achievement is the answer to the question 2, given by Dirac. Observables in quantum mechanics are Hermitian operators in Hilbert space. So this is the core issue here. We will discuss it more in some detail. But before I come to this very interesting discussion, I need to answer question 1. What is the dynamics? Dynamics of the state is just a unitary rotation in Hilbert space that leads to, I will not say rotation, to the motion of projective lines. In particular, if Hilbert space is Cn, the space of projective line is Cp n minus 1. The space that was studied a lot by Maxime Leonson in his lectures. And rotations, correspond to the action unitary of un on Cp n minus 1. In particular, for n equals 2, we have an action of u2 on Cp1. So u2 is actually u1 times su2. So u1 acts trivially, su2 acts non-trivial. So keeping in mind that Cp1 is s2, su2 is a double cover of SO3. And we know how SO3 is acting on S squared. It is just ordinary Euclidean rotations. In general, for Cp n minus 1, un is u1 times su n minus 1. u1 acts trivially, while sun minus 1 acts non-trivially. So it is surprising that dynamics is so simple. In classical theory, we should solve equations of motion that have, roughly speaking, the following form, where phi I is a coordinate on the phase space. Omega ij is a symplectic form. I think it's written like this. Let me call this equation classical. Solutions to classical can be very different. It could be something regular, or it could be something stochastic. Of course, they cannot intersect, but I cannot write it. Okay, probably I'd like to write down some picture. Okay, I cannot draw stochastic. I'm sorry. So it could be that starting from the close points, I can go very differently. I don't know how to. Depending on the type of classical Hamiltonian. In the regular case, we said we have integrable system. In stochastic case, we had dynamical chaos. But it was a classical picture of dynamics. In quantum mechanics, there is no stochastics in dynamics. All motions are just unitary rotations. By the way, it is a second time in physics when going to fundamentals simplify basic equations. First was that when people went from gas dynamics given in terms of partial differential equations to kinetic theory of particles. And here we have ordinary differential equations like classical. In quantum mechanics, we go from classical physics to quantum physics, and classical, that were ordinary differential equations, went to just rotation. Now, it is interesting to see what is the infinitesimal version of unitary rotation. It is easy to write it in terms of psi representatives of the projective line. Psi goes to e to the ith of psi, where h is the Hermitian operator. Really, the Lie algebra of un is the space of anti-Hermitian operator. But anti-Hermitian operator is I times Hermitian operator. What is implied in In a very simple condition QM, evolution in time T1 plus T2 is a composition of evolutions in time T1 and time T2. Note that it is just functoriality of an abstract notion of quantum field theory in one-dimensional case. Okay, so this is why dynamics is very simple. And the final thing that I would like to write is differential equation. I need to match classical equation. Okay, I don't want to move it. I want you to have a look at it. Once again, I would like to say that in classical theory, we do not have a global solution, global in time. We have only differential equation. In quantum mechanics, we have a global solution. But having a global solution, we can write down differential equation. And this differential equation is d psi over dt is I h psi. And this is called Schrödinger equation for evolution of a state. Please note that no h bar appears here. Moreover, psi is just a representative of a projective line. So we need to take S and then induce equations on the space of lines. In particular, change H going to H plus C, this is a constant, does not change the motion of lines. It just changes the representative. Okay, so here I want to make a break, but before the break, I would like to answer immediate questions.
I have a question about the U1 factor. Can I say that the group of symmetry in the Hilbert space is a U1 extension of the symmetry in the projective Hilbert space?
Yes, but this U1 is what people say is not physical. It means that the physical system is actually given by a line.
So I think I can write down a short exact sequence from U1 to the symmetry of the Hilbert space and to the symmetry of the projective Hilbert space. Is that correct?
Yes,
From
but
U1,
it's
symmetry of the
this
projective
sequence
Hilbert
splits.
space. Is that correct?
This sequence splits.
Yes, yes.
So unfortunately, if you will read original papers or conventional textbooks, they do not stress that the state of the system is a projective line. So now we are coming to the most non-trivial concept. Observables is what we observe in a physical system by doing experiments. So here there is a very non-trivial concept. Observable is a Hermitian operator, any Hermitian operator, O. I call it O for observable. In observations in the state that I'll call this way, line passing through psi of an observable O, we get a probabilistic distribution. What does it mean? Yeah, sometimes experiment shows lambda 1, sometimes shows lambda 2, etc. with probability omega 1, omega 2, etc. So there is a concept of the average, and here I write it like this, is sum over I, omega I, lambda I. And there is a formula for O measured here. It equals to trace over the Hilbert space of O, and this, and here I have projection operator on the line, which representative is psi. And this is a key axiom. This axiom could not be reduced from any other axiom. So I call it obs, and this is observation axiom. So mathematically it makes sense. The left-hand side depends on the line, and the right-hand side also depends on the line. Moreover, observation axiom is very simple, but there are consequences of observation axiom.
I have a question. So
yes.
you said that This axiom is cannot be deduced from anything else. But I always looked at this formula as just a consequence of the fact that this average of the expected value of any operator should be a linear functional of an operator, and this trace of operator times something is the most general form of such a linear functional on operators.
Yes.
So isn't this kind of a derivation of this axiom, or there should still be, or the important part is in identifying this projector, this thing we multiply O by with the state, with the projection operator on the state?
Yes. Important part here is the identification. So you are absolutely right that we would like to have linearity. Yes. So you are right that key point here is the relation with the state.
Okay, thank you.
Now, how observation axiom is related to probability expectations. Let us decompose O as sum over I, lambda I, and here we have projections on the eigenspaces. I'll call it projection I. Then observation axiom says that vacuum expectation of O is sum over I, lambda I, and here we have trace over the Hilbert space, and here we have projection I, and here we have projection psi. And this is the expected formula. So we would like to consider this as a probability to get eigenvalue lambda I in experiment. It is very simple and very natural. In particular, it is clear that sum over I omega I equals to 0, as it should be for probabilities. Really, 1 may be considered as a sum over I projection I. Now let me write 1. 1 is a trace over the Hilbert space of projection on the line psi. It works. Now we will try to write down equation for changing of the average of O, in time, d over dt. And here I have O, and here I have psi that depends on t. So that's what I tried to understand. It would be dynamics not of the state, but of the probability distributions. It is easier to go to global picture. So here I have O, and here I have unitary rotation. O of psi of t is trace over the Hilbert. And here I have O. And here I have unitary rotation of the projector. I can take the second exponent around the trace to get trace Hilbert, and we will call this OT in Heisenberg picture. Here we see that we may replace rotation of state by rotation of the operator computed at the same state. Now I can go to differential form for change of the evolutional, for change of the distribution. And I can write d over dt of O psi at t is trace over the Hilbert space. And here I have something like minus I, commutator of H and O, projection on psi. And now I would like to compare it with classical mechanics. In classical mechanics, O may be just some function f on the phase space. So in classical mechanics, we expect that d over dt of f is df over d phi I over dt. That is df over d phi I omega minus 1 ij dh over d phi j. And this is the so-called Poissonian bracket between f and h. So in quantum mechanical formula, I have commutator. In classical formula, I have Poissonian bracket. I need to understand how one can go into another. Here I would like to make an important remark, not the remark, I would say note, that if, we have a family of associative algebras, let me call it AH. It means that AH multiplied BH is CABC, that depends on H, CH, such that for H equal to 0, CAB 0C equals CBA. Then CAB C of H is CABC of 0 plus H. And what do we have here? We have an interesting operation that let me call P ABC plus O of H squared, with P ABC being a Poissonian bracket. It is an interesting mathematical theory that can be proved algebraically. It is the place where H appears not in formulation of quantum mechanics, but in relation to classical mechanics. Idea: consider a family of quantum mechanics depending on H, such that we have OH and HH. At H equals 0, OH, O0, H0 commute. So it seems we have no dynamics. So we will improve. We will consider H physical to be equal 1 over H, and study the following family. Observables would be OH, while Hamiltonians would be H physical of H. Once again, I'll rewrite. So we may consider such a family of theory. Then the quantum mechanics evolution of the average would be O. Here I have psi of t, 1 over H. Okay, I have minus I. Now this is H, and here I have Poissonian bracket. H coming from here and H coming from here cancel. And I will get, so actually I need to correct myself with the I sign. Okay, probably it will be I sign here. So it would be Poissonian bracket of H of 0, O, psi t, plus O of H terms. And this is correspondence between quantum mechanics and classical mechanics. This is how classical mechanics appears. So now let us discuss what happened. I'd like to answer questions, and I will continue on Friday. Tim, do you have any questions?
Well, if you could show that part where the associate algebras appeared, can you scroll up a little bit?
I think you are interested in this.
Yeah.
Okay, so next time we will start with this, making some computations and examples. Okay, so this was the structure, and this is the key theorem. So you may consider it as the announcement of general construction and examples that would come on Friday. Okay, because what you should do, you should write down associativity equation for CABC of H and get the condition for PABC. Okay?
Professor, I have a related question.
Yes.
Okay, here I noticed there's a OH square term, and in the last line of our whole class, can you roll down a little bit?
Sure.
We have HH looks like equals to some H0 and plus some OH term.
Yes.
Are these two results related? I just don't know why the Poisson bracket with O is equal to some H multiply something. Some H, it seems like H multiply some H0, but you write here O. Is
You
it
see,
clear?
Poisson
Okay.
bracket is not multiplicative structure, Poisson bracket.
Yeah.
So here I don't have multiplication. I have a comma. So it's a bilinear operation.
Yeah. Yes. In the last line you write H0, but in the line up upper one line upper you write HH. What is the relation between H0 and HH to
Okay.
make the to make this derivation of the last equality?
HH is H0 plus H times something. So classical physics is a limit, and this is not under control in classical mechanics. We just do not see it. So I hope that this would be clear on Friday when we will consider two things: formal proof of the statement, exclamation mark, and examples. Okay, how to explain something. The best way to explain something is to give a proof and examples. So that's what we are going to do on Friday, not associative. And on Friday, I will give two examples of such families.